Welcome to this second recorded video on the Part A lecture notebook for the fourth module on computational applications. So we will now be discussing our first bracketing method. This is in the Part 2 section of this Part A notebook, and we'll be talking about the bisection algorithm. I provide this link, which takes you to the Wikipedia article that explains the basic idea of this method. So it works on continuous functions. The basic idea is, with a continuous function, if you have a value where you know the function is positive and you have another value where you know the function's negative, well then the function had to have been 0 somewhere between these two inputs. And so what you systematically start to do is cut the interval in half and then reevaluate the function and determine if it's positive or negative. So what would happen with this function, for instance, is you know it's positive, you know it's negative at these two values, and so then you split the interval in half, you'd evaluate the function, and you'd find, oh, it's negative. Well, if this was negative, and so was this one, then the 0, where the function was 0, had to occur between where this new value is and this one. And so then it would cut that interval, this new interval, that is, would be A1 to B2 in half, which would give a value right here. It would evaluate the function there and find, oh, it's positive. So that it should be the new left endpoint instead of this one because it was both positive, and you're shrinking the interval down around where the 0 must be. So you can approximate it with increasing accuracy. So it's a fairly reasonable article to read on your own, this wiki article and description of the method. And if you look through, you will find right away this was the polynomial I was using in the first recorded video for this notebook, and that I used the fact that they said on the article that the approximate root was given by 1.521. Now you know how I came up with that example. It came from this wiki article. So the analysis and a lot of things about the bisection algorithm, it's not a long article, as you see. It's really just got like these 3 sections, this example and the method. And I highly encourage you to take 10 or 15 minutes and just read about this before beginning. But for our purposes, and to keep this video of reasonable length, we will go ahead and start importing all the widgets. And now I'm giving you some suggested activities before we begin. I think you should update the doc string in compute bisection in this function that I've defined below to describe the role of the various parameters and what variables, if any, the function returns. So you should look at what this is, and we'll go over it in terms of what it returns and everything, and think about what a useful doc string would be for this, and also consider adding at least one doc test. So I highly recommend you doing that. It's not required, but I think if you do that, you will understand things much better. So I'm going to first run this, and then we will go through what this algorithm is doing. So for the compute bisection algorithm, it is taking in the following parameters: a function f, a left and right endpoint a and b, and so a should be less than b. If it is not, then we raise a value error and say the bisection algorithm requires that a is less than b. And these should be 2 points such that the function has different signs, SIGN signs. It's positive and negative. Now, it could very well be, and I'll go back to this picture to illustrate, it is fine. It just happens with the way they plotted this function that the function's positive at a and negative at b. But you could graph a function that was negative at a and positive at b. That should be fine as well. The algorithm will work just as well as long as the values at the 2 endpoints are different. Now, how can you check if function value at one point is negative and one point is positive, that they have different signs? Take the product of the function evaluated at a and b and check that it is greater than 0. If that happens, that means the function values had the same sign at both points, a and b. Because if the function value is positive and positive, that yields a positive result. If it was negative and negative, that would also yield a positive result. So if either things happen, if you have 2 of the same types of sign function values, then that should be a value error as well. It said you did not give an a and a b value such that these you have the different signs as required by the bisection algorithm. So you can see this is the error that I've decided to return. And this is as we get to more sophisticated algorithms and functions that we want to code up. It's a good idea to check that the conditions apply for the algorithm to actually work properly. Now there's an n which defines how many times, up to how many times, we will bisect the interval to approximate the root. And there's an interval tolerance that we also set, at which point we will stop iterating. And there's also a function tolerance. So if we find, as you will see below, that if the function evaluation at what we think is the next approximation to the root becomes less than the tolerance we've set here, which is 1 times 10 to the negative 8, we're going to say that's close enough to 0 to stop. We don't have to keep trying to refine the root. So you can play with these or just leave them as their default values. So when we go to perform the bisection algorithm, the first thing we do is say we institute a counter. We're using a while loop because we'll go up to 10 iterations, but we might break out of this early. So under the current iteration, when it's 0, just to track how many times this happened, or if this is even worth computing, we check to see that the current iteration, we add 1. We check if the iteration is less than n at the start of each loop. We add 1 to it, and then the bisection occurs. We bisect the interval. We take c equals b plus a divided by 2. That's the midpoint of the interval. That's defined by a and b. That becomes the new guess for the root. And we check, is it a good approximation of the root? Is f of c, in absolute value, less than 1 times 10 to the negative 8, which is really close to 0? If it is, we break. And when we break, that means we break out of the while loop, and then we will return a, b, and c. So we will return a, b, and then what our approximate value of the root is as the third value in this tuple. Now, if this f of c was not less than the tolerance of f, how close to 0 we're specifying in this tolerance parameter, then we need to determine if either a or b should be replaced with c. So we check to see if f of a and f of c have different signs. If they do, then that actually means that b should be the new, that we should make the new right endpoint equal to c. And otherwise, we need to make a equal to c as the new left endpoint. That might seem a little strange at first, but it's consistent with what this picture is telling us. If you look here and here, this initial iteration produced a b value. This was the midpoint. This was the initial c value, and they evaluate the function in its negative. It has a different sign than f of a. So f of a times f of b is less than 0. We need to replace b1 with b2 to create a new interval that is given by this bracket here, right here. And that's exactly what is being done here. If f of a times f of c is less than 0, then b, the new b value in our interval that we're shrinking down, should be equal to c at the next iteration. Otherwise, we should replace a with the c value, which is what happens, for instance, the second iteration. We have this new interval, we cut it in half, and we see these f of a now, when we multiply it to this, they have the same sign. And so that means that we need to replace a with this value here as a2 to create this new interval as indicated down by that curly bracket. So that is conceptually what's happening, and we keep doing that until either we reach the maximum number of iterations, which is an n, we get a good approximation to the root, or we just simply decide that the way we've updated our interval is too small to continue. And that's where our tolerance on the interval occurs. So I've already run this, and now we can see it in practice. So I'm using that same function f that was defined in the previous part of this notebook, which was given by this lambda function x cubed minus x minus 2. I haven't updated it since then. So now I want to compute the bisection, and I'm going to use the interval 0 to 2. Now, if I only do that, then I'm using the default values of n equals 10, 1e to the negative 5, so 10 to the negative 5th for the tolerance interval, and 10 to the negative 8th for the tolerance of f. So let's see what happens. And I'm returning a, b, and c, all of these values, and I'm printing the approximate root. 1.521, which we know is actually a good approximation to the root of this function. We can also return the tuple of outputs as a single variable. So I'm showing you this. I'm going to say the bisection results, the output of that function is here. I'm going to show you the type of the output, the length of the tuple, and then the last component where I just use the -1 indexing to grab the last component because that's the root. So that's a tuple that's returned from this function. It has 3 elements in the tuple, and the last element is our root. And I can index that also with a 2, for instance, because Python indexing starts at 2. If all you're interested in is the approximate root, then you can use underscores with the commas to basically say, I only want to return the C value, and then there's the A and B values that are returned are just not stored as anything. So then there is the printing of C again. Or here's another way to interact with this function. The function returns, if you know that it's returning 3 things, and you know that the index of the thing you want in the tuple, that it's 2, I could do this. And then that just returns the single scalar value of 2. Or if you knew that you were having this function return a tuple and you weren't quite sure, remembering how many things were returned, but that you only wanted the last one, then you could use that -1. And, oops, excuse me, I must have hit a different key. You could use this -1 indexing. And again, I print that C value that I know all along is correct. So while this shows that the algorithm's working on a function we already know what the approximate root is, we should really add some interactivity. Let's watch what happens if we choose B or A such that f of B and f of A have the same sign. But how to know when that will happen? How do we know when that will happen? So you could refer to the plot. So here, notice how I'm going to interact. I've imported, let's go back to this right here from the IPy widgets, the interact, the interactive, the fixed, the interact manual, and widgets. I've imported all of these different things from IPy widgets, including just IPy widgets as widgets. Now when I am interacting with this function, I'm fixing the function, the f value as this fixed f, and now I'm giving A, B, N, and the tolerance intervals are, the tolerance values are fixed, but I'm letting A, B, and N vary. So I happen to know, by looking at this graph, that if I give an A value, let's say that's, or a B value that's less than 1.5, along with an A value that's less than it, both function values will be negative. Where if B is greater than that 1.521 value and so is A, both the function values will be positive. So let's look what happens when that occurs. So I will make A, let's say B is already at 2, so let's make A 1.6, which is greater than where we know the root is occurring. And notice we get a value error. And you have all the typical type of error things, but what it returns and prints is what we asked the function to tell us what went wrong. The bisection algorithm requires f of A and f of B are different signs. So now, if I, let's say, choose A to be 0 again, and I choose B to be, well, let's say 1.5, which is just slightly less than the 1.52, I similarly get an error because they're now both function values are negative, as I know. So you can see that everything's working as it should. Just because you get an error doesn't mean the code's not working as it should. In fact, this code is working exactly as it should because we should receive a value error that prints this to screen when we attempt to try to find a root between two values where it's not clear there should be a root because the function values have the same sign. So we can also play with other simple lambda functions. But I'm going to say what is going on with all of the errors as we try different values of B in the code below for the lambda function. So that's a question. So here you can say I'm going to interact. The only thing I'm really changing initially is the function f. And notice this is the variable name in this function. I'm not actually creating a new function f that is equal to this lambda function. I am fixing this lambda function as the parameter f in this user-defined function compute bisection. So when I run this, I get a value error immediately with 0 and 2. So you can say, what happens if I move b around? Well, at 1.9, I didn't get a value error. At 1.8, I didn't get a value. Or 1.7. But now I get value errors again at 1.4, at 1.5, but 1.6 I don't. What about 1.2? Okay, it's still a value error. And I'm making b smaller and smaller and smaller. And I'm still all these value errors. So there's many value errors. There's some places where it's not. There's no value error there, no value error, value error. So there's lots of things going on here. What is going on with this function? So just using the interaction with a function is useful to some degree, but it becomes incredibly useful once you start creating plots and use interactivity with the plotting. So let's plot this function to try to understand what's going on. So now I actually create a new function f, and I just want to keep my old one, so I'm not making it so anonymous. I'm making f new equal to this lambda function. And look at this function. It has similar behavior to our original one over here, but then it starts to oscillate like crazy. And that's what's causing the errors. As I was moving my b values around, sometimes it was going negative, sometimes it was going positive, sometimes it was going negative, and so on. So we can plot a different function, for instance, that never crosses the x-axis. Here's a function. It's never crossing the x-axis. It gets close. It's x to the fourth minus 2 times x cubed plus x plus 1. Now, it's very close to 0, but it's never equal to 0. So we hope to get an error when we try to find a root to the above function. So remember, compute bisection is working properly if it gives us an error in this case. And that is exactly what it gives us. It gives us, again, this value error. So again, the take-home message, value errors or errors that functions produce does not mean the code is working incorrectly. It means you are not giving it inputs for which the function can be, that the function can operate on correctly, or can do what it's asked to do. And it's basically saying, wait a second, there are issues here. Now, plots are really useful, and we should often do some initial grunt work on examining the problem we are asked to solve to make sure that we actually set it up properly. So the compute bisection algorithm was not failing just because it output errors. It was functioning just as it should. I know I keep emphasizing that, but it's so important. We gave it bad choices of A and B as the default values in the widget. Simply looking at the plot would have revealed that to us right away. So we are not always able to make plots of functions for many reasons. It might take way too long to evaluate the hundreds to thousands of times necessary to make a reasonable looking plot. The dimension of the space might be too high and so on. But we should always try to visualize the data somehow, in some way, to orient ourselves properly on the problem. That is so important in both computational and data science. We always want to try to get a handle on our data, and we often do that with some form of visualization. So with this in mind, we will create a plotting function that wraps around the compute bisection algorithm to add some illustration to the process. You should really read the comments in this code cell below. So now I'm defining a plot bisection function. It has many inputs that are similar to compute bisection. Additionally, it has some other parameters that are for plotting only. Now, this is the entirety of the bisection algorithm computation. It occurs here where I call the compute bisection function. So this function references this other function, and then it asks for the outputs of it. All that happens below, and I cannot emphasize this enough, is the fancy type of plotting things we've seen at the very first recorded lecture, the very start of this notebook. So we create a figure, we plot the function, I'll add some spaces here, I'll make things nice. And then what we do is we create dictionaries and annotations and scatter plots to help tell the story. So all of this code, even though it looks like a lot, there's just these different pieces of information, much like here, where we want to plot all these various things and explain to the user what's going on so you can have intuition. So I want to leave this for you to read because none of this is actually much different than what I showed. I'm going to scroll up here in that first video that discussed these annotation issues. or the details of this annotation. There's just more details to plot, but a lot of it's just scatter and annotate plots. So I will now run that, and now every time I run this code cell, if you run it multiple times, you want to flush the output to manage the amount of memory you have available on the server. So that's all this does. And now I'm going to interact with the plotting function. I'm going to use our lambda function, that is our x cubed function again, and I am going to use a, b, and n, and I'm going to have a checkbox, and you can see how I coded that in the plot function, that allows you whether or not to show the final interval from the bisection algorithm. So here are additional annotations. With this value of a and this value of b, I'm pointing out where a f of a is and b f of b, the points on the curve associated with the inputs a and b. And then I show the bisection point and the function value at that point and say, well, this is the first approximation to the root from one step of the bisection algorithm. And then I print on the title of the plot what the approximate root is. And now we know it's 1.521 approximately. This is not a great approximation. This is because I'm using one step in my algorithm. If I use 2 steps, notice it's a much closer approximation to where the root is. That's from 2 steps. 3 steps, okay, it overshot, right? Let's look at that again. 2 steps, where here it was 1.4375 and the value is negative. At the third one, it becomes positive. It overshot where the root is because it's just dividing the interval. At the 4th step, boy, it's so close to 1.521. It's 1.515. It's very close now. And then you just start looking at look at these slight changes in the values as you keep iterating. It's getting closer and closer, settling down to that 1.521 value. So you can play with this. And now if you click on show final interval, it shows how the interval is so small now you can't even really distinguish the a and b values. They just kind of are on top of each other. If I go to, let's say 3, those are the final a and b values where I've updated the right endpoint at the nth, at the third interval. The third step of the bisection is now that c value. So you can just see this here again. This was if we look at, here is where we started a and b, and then this was our first iteration. If I say show the final interval, what interval should be updated? We know based on what we've talked about that a now needs to become this c value to make because these have the same sign. So if I show the final interval, that's exactly what happens. B doesn't get updated, A does at that nth iterate. Whereas when I go to n equals 2, what should happen again? That had the same sign as A. A should get updated again. That's exactly what happens. Now at n equals 3, I believe that is where it became positive. So if I show the final interval here, that second update to A, it doesn't get updated a third time, but B now finally gets updated. It gets moved in. So the interval keeps shrinking. So you can play with this and understand it. Hopefully helps you understand the bisection algorithm more and how to make some fancy visualizations and annotations. I know it looks like quite a bit of code, but a lot of it is the same style. Scatter, annotate, and then whether or not you show the final interval or not, it changes what scatter plot or annotation we're making. But it's really just a lot of scatter plots and annotations and some of the basic plots of plotting some axes and the functions, and that's it. There's not a whole lot of conceptual complexity to it. There's just a good amount of code that I kind of copy and pasted and adjusted for each of these pieces. So then I do this as well for this other function, which is the sine of x cubed minus x minus 2. So I'll have that run. It's taking just a second. And you can see exactly what's going on. And so now with this one, with this b value there and the a value there, how many steps does it take for the algorithm to get a good approximation of that root? Not too many. I would say that's a pretty good approximation at that point. Let's just keep going. 5, 6, 7. There we go. Now it's really settled down. 8. That's a really good approximation. And again, it's about 1.521. So now an activity for you. I want you to play with the bisection algorithm. I have broken this up. There's quite a bit to do in this activity, but hopefully it doesn't take too long. I'm just trying to be very detailed in what I'm asking you to do. There's 3 notes here. Note 1, you may want to create additional code cells from what even I've provided below as you work your way through this activity and do various experiments or play with it. Second note, you may need to adjust the A and B and other parameters used for plotting, such as xmin and xmax, excuse me, in order to capture the root for the functions you are playing with or exploring. Suppose the root, for instance, is at 100. Then you need to set up the problem and any associated plots around a value of 100, not around values of 0.5 and 1.75. And xmin and xmax, which are setting the plotting range, 0 and 3, that wouldn't work if the root was around 100. So you have to know a little bit about your problem in order to use this properly. Note 3, it is okay to show examples that produce errors. This is in fact encouraged as long as you explain the errors, but you should also show results that did not produce errors. Now, finally, for this activity, you should do the following. And by the way, whenever you hear me say the word, read the word sum, where I've written it somewhere, sum always means at least 2. I'm hoping that you do 3 or 4, but you should always do at least 2 if I say do some things. So for instance, here I mean test the plot bisection function on some lambda functions of your choosing, both with and without widgets for interactivity. So if you don't do it with a widget, here I'm showing it all with the interaction, but remember I showed how to interact with compute bisection, but I also showed just evaluations of compute bisection that didn't have any interactivity. So you can run plot bisection as a function, just as you normally would, just like I showed with compute bisection. You just have to run it where you give it these various arguments, these various parameters, and it will then produce a static plot. It won't have this interactivity. So you need to do it both with and without widgets, just so that I can see that you can run the plot bisection function, and you need to choose some lambda functions of your choosing, with and without widgets. So if you did 2 of them, have a plot with a widget for a lambda function and do it without a widget for that same lambda function, and then repeat for a different lambda function. And if you want to do more, please do, and I encourage that. Now you should notice that the plot bisection function does not have the tall underscore interval or tall underscore f as parameters. So that means when it calls the compute bisection function, it is simply relying upon default values for these parameters. You need to create an improved plot bisection function in this code cell that allows for all of the parameters in compute bisection function to be set by the user. So the way you do that, the way I would do it, is I would copy and paste this chunk of code from this function here. You would rename it improved plot function when you do it after you copy and paste it. And then you need to include additional parameters of tall interval and tall f into it. And then you need to pass those into here. Now you might want to default those values, or you might want to put them at the end here, because if you default them and then you have non-defaulted values at the end, that's a little bit of a weird way to code. So where you put those parameters in relation to these parameters is something you should think about. And then that's really all I'm asking you to do. It's a copy and paste and a mild edit. And I've pretty much already said what you need to do for that. Then what you should do is test your improved plot bisection function on some, meaning at least 2 lambda functions of your choosing, both with and without widgets, where you show results for different choices of these new parameters. You should use a float log slider for the tolerance parameters. So now that you have new inputs to this function, you need to, when you are interacting with or calling it, with the interaction, for instance, you need to set a slider. Remember, from the previous lecture notebook where I discussed widgets, I described the float log slider. You should really do that for the tolerance parameters, since we often vary tolerance parameters by orders of magnitude when we are testing out an algorithm. So I'm going to stop this recording here. I think I've decided now, because it's actually gotten quite long already, that I'm then going to make a short one for the bisection variant, which is based on called a false position method. And actually, no, it's actually this short, so never mind. I'm going to keep going. Sorry, I'm going to keep going. The bisection variant The basic idea of this false position method is quite simple. It follows 3 steps starting with an initial guess of an interval that may contain a root. So it starts much like the bisection. But what it does is that it creates a straight line between the 2 points a f of a and b f of b. It then computes the x-intercept of this line, which you would call the point c, and it says that's the approximate root. And then it does the same things. It computes f of c and compares it to f of a and f of b and changes the interval just like you do in the bisection, with the exception that you're not necessarily bisecting the interval anymore. So that's the fundamental difference. Instead of using the midpoint of the interval a, b as the guess for the root c, we use interpolation to approximate the function. So if that just seemed like a lot of words, you click on the wiki article, and there is a picture, I know, somewhere here. Here we go. Here's a function that is negative and positive, and here's an initial guess, a0 and b0, for an interval where the function's negative and positive, and the root should be somewhere between there. And look what it does. Instead of just finding where the midpoint is, it makes a line, and then it says where that line is equal to 0, and it's easy to solve for where a line is equal to 0. It's just done this way right here with this formula, so you can just code this one up or this one. That is the new approximation for the root. And then it looks at it and it evaluates and says, nope, not quite 0. And then it iterates very similarly to what bisection does, except it's just using roots of lines. So what I want you to do as an activity is implement this bisection variant. The same 3 notes as the previous activity also apply here in terms of creating new code cells if you want to, and what I mean by testing on some lambda functions, meaning at least 2. So you need to create a function, compute_false, that performs the false position method. Make sure it tests that the conditions are appropriate for running this algorithm. While not required, it is also highly suggested that you also put in a useful docstring and doc test for this function, as those aren't just good coding practices, but they'll actually show me that you understand what's going on. And they'll actually show you that to yourself that you know what's going on. So what you can do is copy and paste the compute bisection function below, edit its name, and you only need to edit a single line of code involving the computation of c, and the wiki article tells you exactly what that has to be in the false position algorithm. Now you should also edit some of the code comments in the docstring because those are no longer correct. So other than edit in a few places, but otherwise it's a pretty straightforward modification of this algorithm. And then all I want you to do is test your code, compute_false, on some lambda functions with and without widgets. This is much like above where I was not using widgets here to compute bisection, and I was using widgets to look at the compute bisection function without the plotting. So I'm asking you to now do that here with and without widgets on the compute false, and then create a new function where you plot it. Plot_false based on the plot bisection function. So again, you can just take the plot bisection function, copy and paste it, or even take your improved one, and then you can play around with it. You can basically just edit a few lines of code, and that's all there is to it. There's not much to edit, actually. You just edit the right few lines of code, and you'll get the nice plotting with your false position method. Now, if you want to get really fancy, try to plot the last line used to approximate the root. This is certainly not required, but it is also not that difficult. You may want to try that actually after viewing the secant method plots method plots in the next part of this notebook, in the part 3 of this notebook. And then I want you to visualize results with some lambda functions with and without widgets. So you're going to test your plot false here with and without widgets on some lambda functions. And then I just ask you to do a comparison activity between these. And so I'll leave you to read those instructions because that's the end of this part. I know this video was a little long, but it was meant to be very thorough and answer a lot of questions because I do know that this can be a very cognitively demanding lecture notebook. And I hope that this helped answer a lot of questions and made it clearer what you're being asked to do at the various parts of this section of the notebook we just covered. So thanks for listening. And the next thing we'll talk about are iterative methods.